In this lecture, we are going to discuss how to improve our model using a process known as data augmentation. Consider this picture of a cat. You and I can agree that it's a cat. Now consider this other picture of a cat. It's pretty obvious that this is the same cat. Unfortunately, while this is easy for us, it's not so easy for a computer. Now, the neural network may be able to identify this because of convolution, but perhaps there's a way to help the neural network learn this translational invariance using data augmentation. As you may have heard, one of the reasons deep learning has been so successful these days is that we have so much more data. Deep learning continues to improve as it trains on more and more data, while other machine learning algorithms seem to hit a plateau. One disadvantage of tabular data is that you just have what you have. If we're doing classification to see if you'll pass my math exam, and I base that on how many hours you study and how many hours you play video games, that can only depend on the data I collected through my survey. I can't just make up new data, which would necessarily include my own biases about student performance. I can't invent a new student who studied this much and played video games this much and then decide if he passed or failed. That wouldn't make any sense. However, images are an important class of data. We can see them. We know that both these images are cats. I know that if I rotate this cat a little bit, it's still a cat. I know that if I flip a car upside down or left to right, it's still a car. Although you should probably be worried if you encounter an upside-down car. In other words, what I'm trying to say is, with images, it is okay to invent new data. Now, here's one problem with this approach. Data takes up space. So the more new data I invent, the more space it takes up. And on top of that, there are an endless number of ways I can invent new data. I can shift the image to the left 1 pixel, 2 pixels, 3 pixels, 4 pixels, 5 pixels, and so forth. And I can also go in the other direction. I can also rotate 1 degree, 2 degrees, 3 degrees, and so on. Do I really want to store all these combinations on my hard drive? Probably not. Also, Google Colab probably wouldn't have space for that anyway. So what can you do? Luckily, none of this work is work you have to do yourself. Have you ever considered how to rotate an image? Well, it's not as straightforward as it sounds. Instead, we can use the Torch Vision API to do all this work for us. To understand how it's going to work, we have to discuss the concept of generators and iterators. For the purpose of this lecture, we won't really differentiate between the two. Consider what you do when you want to write a for loop using indices 0 up to, let's say, 10. We would do for I in range 10. Now in Python 2, you would not want to use range 10 because that would return an actual list of numbers from 0 up to 9. Instead, you would use xrange, which does not create a list, but rather generates those numbers on the fly. That's why in Python 3, this is the default behavior for the range function. If you print out range 10, you will not see a list of numbers from 0 up to 9, as you might expect. Conceptually, that's what it is, but physically, that's not what it is. Instead, it just says range 010, which is kind of not telling us much. A range is a range. Well, it appears to be some kind of object, on which you can call instance methods and so forth. What you might not have known is that you can actually write your own generators. For example, suppose you wanted to write a loop where the loop variable was a randomly generated number. So for x in my random generator would be a loop where on each iteration of the loop, x would be a random number. Can we do this in Python? The answer is yes. We can accomplish exactly this using the yield command. So here is how you would write a myRandomGenerator function that generates 10 random numbers on the fly. As you can see, the code to generate the entire list of values does not have to be computed beforehand. And more importantly, the entire list of values does not have to be stored in memory. Instead, this takes up a constant amount of memory because as soon as the variable for each iteration is computed and used, it is no longer needed. So in PyTorch, when we want to do data augmentation, it's a similar concept. Instead of pre-calculating all of our augmented images beforehand, we are going to create them on the fly. You can imagine that it looks something like this. For each batch of data, we augment X batch using some randomly generated values. Then we yield X batch and Y batch. In other words, only a small slice of X train is ever augmented on each iteration. More importantly, it's done randomly, so you get something different each time, which helps with generalization. What you should notice is that this looks curiously like our data loader, which we have already used for generating batches when we do batch gradient descent. So how does this actually work in PyTorch? What we've learned so far in this lecture is just conceptual. Practically speaking, the answer lies in the functionality we have already been making use of. Specifically, you know that when we load in the CFAR dataset, it's just a function, and this function accepts as input an argument called transform. At this point, you should ask yourself, I wonder what this does. In addition, as you may recall we learned in the last section, the data loader object yields your dataset in batches as you loop over it, applying the transform function on the fly. So to be explicit, what we have to do is modify the transform argument and instruct Torch Vision on how to augment the data. Specifically, Torch Vision comes with a whole collection of different transformations you can apply, such as slightly changing the color, cropping, flipping both horizontally and vertically, rotating, and so forth. I like the idea of changing color because I don't think people mention it that often, yet it seems very important. You would want your model to perform well under different lighting conditions and different colors. I would recommend checking out the documentation and experimenting with each of them in different combinations to get a feel for what has the most impact on your particular dataset. As I mentioned early on in this course, PyTorch gives us a lot of building blocks from which we can compose more complex things. Just like how we can compose complex neural networks from simple layers, we can also compose complex transformations made up from these basic ones. All we have to do is wrap them in a torchvision.transforms.compose object and pass this into the transform argument when we load in the data. Now, because all of the data augmentation transformations are specified in the data function itself, that means everything that happens after that does not need to change. Specifically, consider what the data loader would look like. Exactly the same as before. All the instructions for transforming the data belong to the dataset object itself, not the data loader. If you recall, the only thing that the data loader does is call the transform function on the dataset. Similarly, we should expect that the training loop also does not change. We still have a nested for loop to do batch gradient descent. The first loop is still for I in range epochs, and the second loop is still for inputs targets in data loader. The only thing to be careful about is that while you do want to augment the training set, you probably don't want to augment the test set. Otherwise, you'll get a different answer each time you evaluate it, which is undesirable. After all this, you might still have one remaining question. So far, we've loaded all our image data from pre-built functions in Torch Vision. But what if we have our own image dataset? Sure, I can load images into NumPy arrays using a library like Pillow. But once I've done that, how can I apply these transformations that Torch Vision provides? It seems like, in order to use them, I must have a Torch Vision dataset object. Luckily, we will cover this later in the course, but for now, you'll just have to wait and see.